My mouth is on fire. Why did I eat spicy food? Oh my god, it was so fucking good though. Worth. Alright. Spicy food is the best? Hell yeah it is. Thank you for putting this on. No problem. I mean, we'll see how it goes. Kind of winging it here. Alright, let's see what we can do here. See if we can make some magic happen. I'm gonna find some music we can put on the screen. And yeah, what am I gonna jam out to today? We'll see what YouTube says for playlists. Countdown to getting a Tandoor oven? Oh my god, dude. So I have this idea, because I have like a relatively large backyard, and I was thinking about extending my deck with an outdoor like pizza oven. Where I'd build like a round stone like pizza oven sort of thing outside, and it would double like just as a gathering area. But a Tandoor sounds fucking amazing. Is Python easy like Python is much easier. Python's what a lot of people use to start programming, which is pretty sweet. 4:28 a.m. in India. Well, good morning and good evening. I just had some Indian food, which is one of my favorite cuisines. Absolutely delicious. Rust, is some stuff easier than Python? Yeah. I mean, I would say types are easier, even though they make it probably, like, technically harder. It makes it, like, design easier. You don't have to figure out what the arguments are to everything. I like that a lot. Python's easier to get wrong. Oh, for sure. Started with C. C's a great place to start. I haven't written really any C in the past 3 years, because Rust kind of just supersedes it for at least my use cases, but it's pretty neat. Vectorized emulation on day 5. I mean, we'll probably talk about it on like day 2 or 3, but we're probably not gonna do anything with it. Well, we're gonna probably use it. We're not gonna write it. There's no way. We don't have time for that. All right. So welcome to Fuzz Week, day 1, the week where we go through random fuzzing things, and I yawn while giving an intro. So what we're gonna do is we're going to try going through just some of the basics of fuzzing today. I have a blog post, which I probably should post a link to, but we'll go check it out and see kind of roughly what I want to go through. Now, it's really important to note, nothing here is scripted or planned. I don't even have bullet points. I don't have slides. I don't have any material I want to go through. We're just kind of winging it. And I feel like that's the best way to teach fuzzing, because you don't get a script when you're fuzzing. There's no guide. There's nothing telling you what to fuzz. There's nothing telling you what aspect of the code to look at. There's nothing telling you when to stop code auditing and start fuzzing, or when to write your fuzzer, or where to hook in your fuzzer, or how to catch your crashes. You kind of have to wing everything, and that's a really important part about fuzzing, and honestly security research in general, is the ability to adapt and the ability to feel not necessarily confident when you fail, but to not feel super torn down when you fail, because security research is pretty much just failing continuously, and a lot of the skills that you get kind of center more around failing faster, or understanding when something is starting to go awry and trying to avoid failing sooner, but you're going to still probably fail. Ultimately, you just get a target that's too hard, or you can't find any bugs, or you don't have a way of emulating the target, or you can't get coverage, or AFL doesn't work on it, or it uses a custom compiler that you can't use existing instrumentation. It's pretty common that you just can't do a lot of things the way that they're intended. A lot of the public research out there for fuzzing typically assumes a couple things. And this is, of course, not... There are tools to cover these edge cases, but most fuzzing out there assumes a couple things. 1, you're working on Linux. 2, you're working on a system where AFL works. 3, you have fork. 4, you have source to the code base. 5, you have source to the code base and you have a build system which is capable of building it. 6, you have source to the build system and a build system that's capable of building it. And the build system is simple enough that you're capable of replacing the compiler that is being used to build that tool with a replacement compiler that might have slightly different behaviors, but it won't matter enough for it to actually break the build system. And at that stage, you now have a binary that has some instrumentation in it, and you can use AFL. But if none of those things are true, you're basically forced to use something like QEMU, or AFL QEMU, or QEMU AFL, and it's just radically worse of an experience compared to AFL, just the standard, proper, source-driven way. It's great that there are alternatives, but those really struggle in some of the more complex cases that you need to work with. And that's some of the things that I want to address here. I want to show how easy it is to write your own fuzzer and how you don't really need to be tied to a tool that's tied to a system, because you can quickly make a new fuzzer for a different environment if you need to. So let's see. Can you keep the whole corpus in RAM? Oh, of course. That's what I always do. What is AFL? We'll get into that in a few minutes. Well, I don't know. Maybe a little bit after. I'm trying to figure out if I want to talk about AFL first or if I want to just talk about fuzzing first. But AFL is a public fuzzer that a lot of people use. Okay, so this week we're going to stream 5 different days. I have no idea how long the streams are going to be, probably 4 to 8 hours. And we're going to talk about a couple different things. So today is July 13th, and we're going to go through some of the basics of fuzzing. And in here, we're going to just talk about roughly what it takes to write a fuzzer, how fuzzing works, what it is conceptually. We're going to talk about public tools that do fuzzing kind of for you and that a lot of people build around. And when that happens, what are the weaknesses? When do those tools fail? When do they work well? When do they not work at all? Tomorrow we're going to cover a little bit more about code coverage, which is a really common technique for extracting what has been hit during the fuzz case, observing kind of what has been exercised in the program. And then after that, everything is completely up in the air, and we're likely going to start looking at performance. We're going to look at the behavior of targets under test. We're going to look at scaling to multiple cores and multiple servers. We're going to talk about writing custom fuzzers and mutators, collecting corpuses, all these different things that kind of go into the bucket of fuzzing and a little bit more advanced fuzzing. But I would like to say that I don't think fuzzing is really advanced yet. I don't think there's really anything in it that is very difficult. So I don't think there's really anything there that can't be followed along. I think a lot of aspects of fuzzing that sound difficult because they're in a paper. And in a paper, you don't use easy-to-read terminology. You don't describe terminology. You assume people know these things. And it kind of leads to this imbalance where people think the advanced state of fuzzing is really complex and really sophisticated, when ultimately a lot of papers can be summarized with add a little bit more instrumentation to determine when certain memory is being accessed and log that and then save files if it's a unique thing being accessed, right? And that could be a 10-page paper. They're going through how it works and how they implemented it and the performance properties and all those things, but ultimately those don't really matter for using it. Obviously, you want to pick something that scales and is usable, and those are the sorts of things I nitpick out of papers. But when it comes to just like the idea itself or the implementation of the idea itself, typically not very difficult. So, all right, gonna talk about libfuzzer? Maybe I will. I think that's something we could probably talk about. Can't believe AFL developed by Google security engineer bottlenecks on expensive disk I/O. Like, why? I have no idea, honestly. We'll probably talk about that. I like ripping on AFL. It's important to note that when I'm ripping on things, I understand where they're really useful. I'm mainly nitpicking things that I think should have been done much differently from the start. Okay, let's see. All right. Let's go and take a look at kind of, I don't know, what does Wikipedia have to say about fuzzing? Let's see if Wikipedia defines it well. So, the Webster's Dictionary defines fuzzing as, let's see what they say. Fuzzing, or fuzz testing, is an automated software testing technique that involves providing invalid, unexpected, or random data as inputs to a computer program. The program is then monitored for exceptions, such as crashes, failing built-in code assertions, or potential memory leaks. Typically, fuzzers are used to test programs that take structured inputs. Yeah, I think that's a relatively fair way of putting it. Effectively, with fuzzing, I want to take inputs to a program, whether that is a protocol that's being sent over a socket or over a network communication line, or I want to take a file that's stored on disk and it's loaded by a program, maybe a game save file, maybe a PDF for a Adobe Reader, maybe a web page that's sent to you over the network, all of these different things. And typically what you'll do is you'll take these valid formats and you'll modify them. You'll put random characters in them. You'll turn a curly brace into a square bracket, and you're just randomly mutating this input, and you're attempting to load the program that loads the original one and see if it misbehaves. Pretty much in all circumstances, you're looking for crashes. It's pretty hard to get more information other than crashes, although we will talk about that at some point. But yeah, effectively, you're just trying to run random inputs through a program. So let's start off with a really simple example. And to do this simple example, I need an example thing to fuzz. And I feel like a good place to maybe start out here would be, I think we know that strings has bugs, right? I think we know that strings has bugs. Or like an object dump, I think has bugs. I think we know like a couple of these things have bugs. We could also look through papers to see what things people are typically looking at, but I think we could take I don't know, so this is a hard part of fuzzing, is figuring out what you want to fuzz. If you're a black hat, it's exceptionally difficult because you're trying to figure out what would get you into a system the easiest. When you're a white hat, typically you have a manager or a boss or a company that develops a piece of software, and obviously you're going to fuzz that thing. Now you need to figure out what components of it you want to fuzz, but you at least have a little bit of guidance. So, let's go grab, I don't know, let's take a look at object dump, which is from binutils. Oh, you know what? Actually, this is not trivial to build. It's easy to build, but it's not trivial to build. I mean, we can go through that process of kind of building things. Image magic, is that easy to build? I feel like I like binutils because it has like a lot of things where it won't necessarily build. So this has strings. This is a bunch of shit. I think this is a great place to start because there are so many different things. So we're going to go to binutils, and then we're just going to go, we're going to sort this by date, and we'll grab something from like, I don't know why there's such a big gap. Was it really that long between releases? Because I'm kind of scared that the 2003 version might not build, but let's try it. Let's see if we can build a 2003 piece of software. This might be relatively difficult. Okay. Let's W at this. tar xf binutils. Alright, are we going to be able to get this to build? I feel like this is easier than... Since it's 2003, I'm not building this with jobs. That's a bit risky. Is this actually 2003? God, will this build? As long as there's no warnings as errors, this should probably build. Otherwise, we can add W no error in the C flags. Okay. Are we going to cover... Someone asked about Windows, I think. If we're going to cover Windows, not, like, really directly, because ultimately, Windows and Linux are pretty much the same process for fuzzing. I mean, we could look into it, but everything that we're going to do here will just literally work on Windows. Obviously, building binutils won't necessarily work directly on Windows. You'd have to use Whistle, or you'd have to use, like, Cygwin to build it. But it does work, right? Nothing that we're doing is going to be OS dependent. I really hate that concept of, like, all these fuzzers working only on Linux. And a lot of that comes down to they use fork, or they're too lazy to develop the code base and spend a little bit extra effort adding alternative ways of doing things. Okay. Rate type has incomplete element type. Well, that's gonna be an issue. And I have no idea where we were. Looks like we're in gas. Well, let's see if we found it to object dump. If we found our way. Oh, that'll do the trick. Yeah, we didn't get a full build, but this looks good enough. So we got a 2003 version of object dump, which is absolutely fantastic. Fuzzing is generally much slower on Windows. It's not at all. That's just based around people using fork for fuzzing, which is just not necessarily a great way to do fuzzing. We built things, yeah. We only built some of it, but you know, whatever. This probably is not stripped. I doubt it would be. I don't know if it's built with optimizations, but I don't care. Okay, So now we're at kind of an interesting stage of fuzzing. We got our program, we built it, and in a lot of situations, the program's already built. You're using something that you downloaded or was provided to you or is closed sourced, or who cares? You already have a binary that you're capable of running. If you have a binary that you're capable of running, you're already basically in the 95th percentile of fuzzing. A lot of people are in that exact same boat. You have a binary. We're not assuming you have source here. Obviously, we built binutils, but we built it such that we could make an old version. We didn't build it because we actually needed to, right? We could have used the object dump on the system. We're just wanting to use an older one that's easier to crash, and also, since we're doing this on stream, is less likely that we come across a bug that actually works on modern binutils. This is 20 years old. If we find a bug here on stream that is an ode and modern binutils, look, there's only so much we can do. We're using a 20-year-old version of binutils. We're trying. Okay. So, effectively, in a lot of situations, you have a binary that you're capable of running. Now, in more advanced fuzzing, and we'll cover this later in the week, sometimes you don't have a binary that you can run. Sometimes you don't have a binary at all, and if you do have a binary, maybe you can't run it. That happens a lot for embedded devices. For example, I can go rip the firmware off literally any device in my house. I can just go desolder a chip, throw it on like a E2 PROM reader or a ROM or RAM reader or whatever the fuck I want to use, and I would be able to extract the firmware. At that point, I'm not able to use it. I don't necessarily know how it's encoded in that firmware. I can maybe figure that out. I don't know where it's loaded into memory. I can probably figure that out. And then at that point, I don't emulate the devices or even know the proprietary environment that this code runs in. So I'm likely not going to be able to boot it at all. And this is a part of fuzzing that's very difficult. Effectively, there's nothing out there publicly that can really help in this environment. Almost everything out there for fuzzing assumes that you have something you're capable of running. And in a lot of situations, that's not the case. And when I say a lot of situations, I mean like 5%. But I mean, a lot of people run into that problem and either promptly avoid it and just don't look at that surface. It's pretty common that people reverse engineer the code and find that it uses image magic internally in the firmware, and they will go build image magic and fuzz their own version of image magic and then try those bugs against the real target. Anyways, so thank you, Blue Hex Source, for the Twitch Prime. Hell yeah. Can we run object dump on object dump? Probably can, yeah. Okay, so what have we done so far? We went and we found a target. We've decided we want to fuzz binutils. And if you're not familiar with binutils, this object dump thing that we're looking at right now is capable of doing a couple basic things with different binaries that have been built. It can tell you the headers, like where different sections are loaded, how big those sections are, whether they're the text section, which is the code of the program, the data section, which is the data of the program, RO data, which is the read-only data, like where the strings end up being. And this can tell us a lot of information about that binary. It can also tell us information about the debug symbols in it. This is not stripped, so it has something called dwarf, which is the debug format that's typically used on Linux. And this can go through and it can just tell you a lot of information about a binary. So let's go and use it on itself. So we're going to object dump, and we're going to say, I want to know what the archive header information is. So at this part of fuzzing, that we have something that works, we need to figure out, what do we actually want to fuzz? We have the program, right? And you might be thinking, oh, well, we know. We want to fuzz object dump. But we don't necessarily know. Do I want to fuzz archive header parsing? Do I want to fuzz the disassembler? Do I want to fuzz the debug information aspect of it? Do I want to do all of them? Do I want a random chance of picking different flags and pass those in to see how it behaves? And a lot of times this is driven by as an attacker, you might not get control of that. For example, let's say object dump is on a server and it's disassembling files you upload to it, and then giving you the results back. In that situation, you don't really care if you can find a bug in fuzzing archive headers, because the only thing the service is allowing you to actually do is to fuzz the disassembler. And at that point, you're going to have to fuzz with the D flag. So if we look at what happens is when we use this flag, it will print the disassembly for the program. And it's a lot. It'll just keep spewing forever. But we can kind of look at some of the other things. Let's look at the headers. This is going to tell us information. I guess, is this statically linked? I don't know if it is. File headers. Kind of interesting. It's telling us where it's being loaded at. It's telling us the architecture of the binary. Debug information, which interestingly doesn't seem to work, which we might have to build this with a compiler that's slightly... well, we might just have to use C flags that are older. Now, this is not a problem that you would really have when you're doing modern things, right? But since we built such an old program that we're using to analyze programs, but we used a modern compiler to build it, it's actually not recognizing a couple things about it. Let's see if we can find, let's try it on like something else. Yeah, there's no debug information on that. So Intel syntax or AT&T? Only Intel. Intel's where it's at. I mean, what we just saw, this was AT&T, if you're asking that. But I only do Intel syntax, because it's just what I consider to be a lot better. Huh. Does this work? -S? Probably not, because we don't have debug information. So there's a way, when you build things, -G provides the flag to say build this with debug information, which basically puts in the binary some communication of what source was used for which locations in the file, and it helps with debugging because it kind of tells you where different things were taken from in source and placed into the binary. It's really important to see that. But we're having some issues with the type of debug information, and that's very likely due to the debug information being too new. So let's go take a look at, we're going to see how we can set the debug flags. So, okay, so what we want to do is we probably want to generate dwarf symbols, dwarf debugging information, and we want to do this with an older version. So let's see like dwarf version 2. I'm trying to figure out dates of when these things came out. This looks like 93, so I'm sure it handles that. Dwarf 3, 2005. Okay, so we're going to do dwarf 2. So we'll do -G dwarf version, make clean, configure, and then C flags. And something that I commonly do when I'm trying to build something is I just put in a bad flag, and I see if it actually takes that. And it seems like it does, so it probably is honoring that. gdwarf 2. Let's build it without optimizations, debug information, and then we'll use dwarf version 2. Okay. AT&T is easier to read in every way. I completely disagree. You need to use like special characters for registers and for constants. It uses instructions that don't actually exist in x86. So it does look like my flags did end up making it. Okay, so we'll go into bin utils, and now we should have, let's see now, if we can object dump. Oh my god, we can't. Why? That finds a bunch of dwarf information. Do I need to tell the linker that as well? So we're just trying to get this to build in a way that it works, because since we're working with such old software here. I wonder if it's, let's see. Yeah, I don't know why. And I don't want to build an old compiler. That's just going to take way too much effort. Huh. I don't even know what it supports then, if it doesn't support dwarf 2. But I could totally see it be the linker where that's a problem. Symbol table? Okay. At least we have some stuff. And is that demangling? I don't know if it is. Well, this is C code. I don't know if there's any C++ here. Okay, well, whatever. We'll try and see if we can just start making this work. Oops, object dump, supported targets, all these, supported architectures, and it does support x86-64 apparently. Full content source. The disassembly might have bugs. I feel like the file headers would maybe have bugs. Probably one of the least likely things. So I think what we're gonna do is we're gonna write a fuzzer that will do that will kind of try different options. And it's dynamically linked. I might see if I can statically link that. I mean, it doesn't matter too much. Okay, so we're gonna take the object dump that we built, and we're just gonna move it back a couple directories, and we're gonna make object dump fuzzer. And in the object dump fuzzer, we're going to start working on a harness. So the harness is effectively the part of the fuzzer that is going to run the program and observe crashes if there are any. In our situation, we're actually going to ignore crashes from the start, and we're just going to have it, like, we're only going to have this thing run the input file through. We're not actually going to do anything crazy with it. We're going to make one folder called corpus, and this corpus is going to basically contain the files that we're going to use to load into this object dump tool. And these are just going to be whatever ELF files we can find, and we're going to have object dump try to load them, and then we're going to corrupt them and see if we can get a crash to happen. So we're going to take these files from user local bin, user bin, perfect. And here we're just going into user bin, and we're grabbing a bunch of files, a bunch of programs that exist on our system already. And most of these are elves. We could go and try and prune these down. Find star xargs file, and then look for things that are not elves. And how will I remove these? Is there a good way to do that? Params to find. I like this one. Cut D:(F1). Yup, I like this. Okay. So now every single one of these files says ELF. Which means all of these are some binary file that exists on the system that object dump is capable of disassembling and doing other things with. So what we're going to do is we're going to make a simple script in Python, and we'll do this in another terminal. Manutils, fuzzing, objjump fuzzer, and we're gonna do fuzz.py. And in here, we're going to figure out all the files that exist in our corpus. So let's do corpus file names is equal to import. Is it readdir? I think it's readdir. Python 3 fuzz. Readdir? Lister? You can also do glob. I never do glob, and it's good, but I just haven't gotten used to it yet. Okay, so now we're gonna basically glob.glob. Okay, let's try glob. I like when chat suggests things that we try and use, and glob you can basically, I think, it'll give full paths, which I like, or it'll use like file objects. Okay, and then /star, I think. There we go. And this is exactly what I wanted because they're full paths, which is fantastic. So this is going to be get a listing of all the files in the corpus, right? And the corpus are the files. The corpus is the files, the set of files which we preceded the fuzzer with to give it valid inputs. These are files that the program should be able to handle parsing that we will ultimately mutate and splice together to try to find bugs. Okay, so now what we're gonna do is load the corpus files into memory. Now, you don't necessarily have to load them into memory, but it's going to mean that we don't really care about the layout of things on disk, or how we organize things, or how we handle temp files. We're just going to load everything into memory, and we'll write the file out, and then we'll run it into the program. Performance is not perfect with this, but once again, we're trying to demonstrate the very basics of fuzzing. Bitcode giving a gift sub to M4SS7. Mast? Thank you so much, Bitcode. Pathloop does just about everything. Oh, interesting. In before object dump fails on one of those? Yeah, so the first thing that we're going to do is we're actually going to run the corpus through without any modification and see if there are any crashes. Since we're working with such an old version of object dump and with such new versions of binaries, there's a chance that things might just crash. Better have a good fuzzer than a fast fuzzer? Yeah, I totally agree. Okay, so this is our corpus, and I'm just going to do an array here. You could do a set, because you could eliminate some files which get copied. Honestly, we'll start with this set. And then we'll do for file name in corpus file names. Corpus, is it .add? I think it's add on sets in Python. I always use update for some reason. Okay, so we'll print the length of this, and we'll print the length of corpus. And there we go, we lost some files, which makes sense. The reason that we lost some files is because some of these are probably aliased or were symlinks to the exact same binary, but with slightly different behavior. So great, we only care about the raw binary, not the way that it's being used, because we're only passing this into an application that parses that. So we're then going to convert that back into a list, and now we will have, we'll say, convert the corpus back into a list as we're done with the set for deduping inputs which were not unique. And now that we have a list, it's just a little bit easier to think about. It's just a linear thing in memory that we can index with a number. Now, we have, wow. We have an object dump here, and this is what we actually want to run. So let's figure out, let's do a basic thing, and we'll have it dump the file headers. So we're gonna make a def fuzz, and this is going to, is it def? Oh my god, I haven't written Python in a long time. I haven't written Python in a long time. I often, when I'm writing Python, I don't actually use functions. Why am I spacing? It is def. It's def. Okay. Whew, whew, whew. Okay. Problem is most people often focus on optimizing. Okay, well this is something that I'm actually going to cover in this week. I pretty much only focus on the performance of my fuzzers, and I find that I get much better results than people who focus on writing really good fuzzers. I don't know if there's any validity there, or maybe what I consider a crappy fuzzer is actually a really good fuzzer. It's hard to say. I'd like to get to the bottom of that. But I've definitely solved a lot of problems with just perf. Okay, so in fuzz, this is going to be run one fuzz case with the provided input, which is a byte array. So we're going to have a byte array that we pass in, which is input. We'll call it inp. And what we're going to do is we're going to, we need like a temporary file name, but right now, so we want to make this thread safe, right? We want to make this run in a way that we can use multiple threads because it's just better. Now the question is, do we want to do that right away or do we want to do it after the fact? And I typically recommend that you do it right away. And that might sound stupid, but typically re-architecting a code base to work with threads is a lot more difficult than architecting it kind of correctly from the start. So we're going to have the concept of a thread ID here, and when we start the fuzzer, we'll just pass it a unique thread identifier, and then we'll pass it an input. In this case, we'll just pass it ASDF. And let's do, you can do this, right? I'm going to try this. Class bytes. How do I check if it's bytes? There we go, there we go. Is instance. Why would I use that over this? And why are there a million ways in Python for me to do things? Is instance in bytes, okay. Assert that that's bytes, and assert that this is, what is a number? What is a number? Int? Okay. You know, like that, it's a little bit clear what I'm expecting, which is fantastic. And what we're gonna do is we're going to, open, here we'll use a format string, temp thread ID, write binary as fd.write input. So this is write out the input file write out the input to a temporary file. For making temporary files, see temp file. I actually don't like using temporary files like that. I like having full control kind of how that works. And we'll say this is a temp input just so it's a little bit easier to RM. But I like being able to take a peek into what was produced rather than having it go in a temporary directory, which is kind of harder to end up finding. I think you can type this? Is that a Python 3 thing? It's valid syntax, okay. Well, that's fucking sweet. I mean, that's a very confusing error message. Oh, did I screw something up? Yeah, I did. Okay. I was about to say. I mean, that doesn't seem to care. Oh, they're not checked. Well, why wouldn't it just assert that? Why doesn't it just do, whatever. 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 Okay, so that's going to save out the file. Oh my god, okay. There we go. And then that way it won't end up creating a temp file that we don't expect when it does this, because this will just fail the assertion, which is fantastic. Okay. Types in Python makes me dislike Python. Oh, I only like types. Types are just amazing. Okay, now we've created this file, and what we want to do is we want to have the program load that file. And to do that, we have to run the program. So let's take a look at subprocess, and we're gonna run the program using subprocess, check output, and then we pass in object dump, and let's just see if this works first. I forget what this returns. I think check output returns a tuple of the looks like it's a tuple. I'm guessing it's standard out, comma, standard error. Let's see if that unpacks correctly. Too many values to unpack. Does it give a status code? I wouldn't be surprised if there's a status code, but I don't know where it is. It's just standard out. That's fair. Okay. Okay, so now we have the output. So this is going to run object dump until completion. And I guess we might have to p open this. Let's do that. So we'll do subprocess sp.wait. That's gonna wait for it to exit. And we should be able to do sp.status. And we're not hooking standard out right now, which is actually fine. Is it exit code? P open, poll, wait, communicate. Oh, wait, return, says the return code. That's Python 2. Yeah, this hasn't really changed. So this will give the return code. Sweet. So we're going to assert that the return code was 0. And this is going to be assert that the program ran successfully. Now, it's very likely not going to run successfully in many situations. So if we end up running this will probably fail to run. Yep. So we're going to assert that the error code is greater than 0, which I think crashes use like negative numbers. So we're going to just assert that it's greater than or equal to 0. Now, we could also be more strict with what those return codes are, and we could just see what it's like. Okay. We're all backseat programming. It's Twitch's programming. Yeah, of course. Only like 2 of us even know Python. Isn't 0 for success? It is. But in the case of like an invalid file, I mean, we can try and go strict, but this is likely going to fail very soon. But who cares? So we're gonna then ask this to disassemble, and we'll do tempfn is equal to this, and this will be tempfn, and I'll have it disassemble the tempfn. And now it will print the disassembly of that thing. And in this case, file format not recognized, right? So in this case, let's just print ret. In this case, we are getting a failure code that isn't due to it crashing. And I'm pretty sure the OS will return negative numbers if it crashes, so we're just gonna do this. Perfect. File format not recognized, no surprise. So now we're gonna do while true. We're gonna grab random, and we're going to pick a random input from our corpus. And to do this, we'll do selection is equal to random.randint 0 to, and it's inclusive, len corpus -1. And then here, we will call fuzz as thread 0 with corpus selection. And I think there's random.choice, actually. We can do this. Okay. And here we go. Now we're getting disassembly, which means we're bottlenecking on output. So we're going to have this go to dev null. And what's the best way to do that? I mean, I can pipe it and just not accept it. Might be the best way to do that. Let's see what we can do here. And then we're going to print case in range k. And we'll start with here. Print fuzz case complete. We're just printing a status message so we can see if it gets stuck. And it looks like it's getting stuck. I think with... Oh, there is subprocess dev null. Sweet. Because I think it was waiting for us to read some of the standard out. Okay, dev null, 2 L's. Can I just change that to a 3? Dev null, 2 L's. There we go. We're fuzzing. Look at that. And then here, I should be able to fail with a... We'll say this. If ret is not equal to 0, print exit with ret. This way we actually see what's happening. Yeah, and it seems like it's getting stuck. Okay. Have none of these failed? Yeah, I guess all of these are valid elves. Cool. And there we go, we're fuzzing. out here fuzzing. All right. Well, look at that. Okay, so we're gonna switch this over to a different server. This server might be shut. Okay, it's not. What is this? Okay, this is gonna be slow, but whatever. I shouldn't have scooped it. I should have rsynced it. But I don't think this is gonna take too long, so I'm not too worried about it. Yeah, we're already on the object dump. There we go. So now we're gonna set up the same environment. Do we have the code on the left or right side? I think the left side. This way it doesn't make my gaming computer get really loud that I'm streaming on, which I just hate when it's loud. Okay, so we're fuzzing. We have fuzz cases getting completed. Let's pull in some statistics. So this is what I would say is very, 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 very important, is understanding the performance of your fuzzer and understanding roughly the how many fuzz cases you're getting. I highly recommend. I'm doing this before I even have this catching crashes. I'm trying to figure out how fast. So what I'm gonna do, start is time.time. And this is get the time at the start of the fuzzer. Okay, now what I wanna do is when a fuzz case is complete, elapse is equal to time.time minus starts. Determine the amount of seconds we have been fuzzing for. And then we'll do like the Linuxy style things, which I actually really like this format. We'll do this. We'll print cases. Now we're kind of printing these as stats. So this will print the uptime, and I need an F here. There we go. So I see the time that the fuzzer's been running. And then we see the number of cases that have been performed. And then I'm going to say the fuzz cases per second. Determine the number of fuzz cases per second. And this is float case divided by elapsed. The fuzz cases divided by seconds. And this is FCPS and 10.4F. And that's probably unnecessary precision, but whatever. Okay, so now we see the number of cases performed, and the number of fuzz cases a second. So it looks like right now we're getting about 10 inputs run through the program every second. We still haven't added any corruption to this, where we're mutating or affecting these bytes. So we're going to get to that shortly. Let's get this working with threads quick. And the way that we're going to do this is threading. And I always forget the syntax for this. Always forget the syntax. Threading dot thread, and this is probably not going to scale because it's Python. So we'll do threading dot thread, and the thing that makes no sense to me is that the group and target or the group is first, so you can't just have it be the function that you want it to run. So what we're going to have is def fuzz worker. We'll just call this worker, and to do this we'll say global start corpus. That looks pretty good. And then we should be able to threading.thread, target is worker. This will take a thread ID, which will pass in here. Args is thread ID. For thread ID and 0 range, let's just do 4 for now. And then while threading.active count is greater than 1, time.sleep 1.0. Or 0.1. You like that? You like that way of checking if all the threads are complete? I do. Okay. Gotta love that gill. Yeah. Okay. Oh, yeah, and then you have to do dot start. Nice. So now we have 4 workers running, and they're printing their own different fuzz case numbers. So we'll just do cases, while true, cases plus equals 1, update number of fuzz cases. We're hitting the gill really hard here. Total number of fuzz cases greater than 0. I don't think so, because I think the main thread counts as a thread in Python. Let's try it. If we do 0, this will likely exit immediately. Oops, cases, and then cases. There you go. Now we're getting 60. Wait, why is that going down? Oh, because some of them are getting stuck. So it looks like we're getting more perf, which is great. And then Control-C never works in Python, which is fantastic. So it does look like active count greater than 0 does work. And then we'll just do number threads 192. Do you need a lock for cases? I don't think so. Okay, so this is not scaling, with cores. No surprise, because we have a big lock. Basically, that whole corp, like, we're just not scaling at all, which is annoying. Thank you so much, Jocular, with the 3 months of sub. Thank you so much. Do you need lock for case? I don't think so in Python, right? Because everything's locked. We also have, we have file IO problems, which are gonna suck. Anyways, I mean, it's like kind of working. It's kind of working. Okay, so let's start mutating these inputs. And can we mutate a byte array? Are these byte arrays already? If I read them as bytes, is that a byte array or is that bytes? Because byte array is the one that you can mutate in place, right? Because I don't want to make a copy. It's a byte string. So I need to make them byte array. And then where do you get byte array from? Where do you get that from? Oh, unhashable type. Oh, well, I guess we'll just, how do I do this? List map byte array. I forget if you use the function first. Is that doing it? Okay, there we go. So everything's all good and dandy again. Okay, does everything make sense to everyone so far? We load up all the files that we seeded from the corpus, which is just user bin. We loaded them into memory just because it's more convenient, not actually because of perf. In Python, we're not really benefiting at all from this perf, and we're still writing it out anyways. We start a timer. We have a total number of cases, which is just a statistic. We run a fuzz case. In all of our threads, we run fuzz cases. We update the number of fuzz cases that have been run. We determine the amount of time we've been fuzzing. We compute the fuzz cases a second. These are all just stats here. This is just so we can print some statistics. We start up all the workers, so we have threads. And in the fuzz case, we write out the input that we randomly picked from our corpus to a file. We then run that file through object dump to see if it can parse it, and then we exit out when it's done. So we're going to take a look at a little faster flag for object dump. Let's take a look at dash maybe F, or actually X, all headers. Parse all the headers, but it's not going to disassemble, so it'll probably be faster. It's not faster because we're in Python, and we're just failing to scale at the Python level, which is great. That means we actually can justify writing this in Rust, and we can show you why that's important. And time.time minus start. Okay, I don't know, maybe we're bottlenecking on object dump. Highly doubt it. So, one thing that's important that I should go on a tangent to describe right now is when you're fuzzing, you can't always thread things the way that we did. Sometimes you're just not able to run multiple copies of a program. Maybe it drops a lock file to disk. Maybe it accesses a settings file or something that can't be opened multiple times. Or maybe it gets changed and it would get corrupted if you had multiple copies open. In our case, we just know that object dump is a standalone enough tool that we are able to run it threaded. But if you had a program that doesn't fundamentally run multiple copies on a system, maybe it's a daemon, maybe it's a service, maybe it's something that drops a lock file or a PID file or reads some settings. There's so many different reasons, or maybe opens a specific pipe or socket or binds to a specific port. There are many reasons why sometimes you can't run multiple copies of a program. And in that situation, you pretty much always have to fall back to emulation to get scaling, or using virtual machines where you actually are running multiple OSs. We're going to talk about that later. I pretty much never like to fuzz in the way that we're fuzzing right now. I don't like fuzzing. I call this live fuzzing, where we're fuzzing on a live, real system. We don't have determinism. System noise is interfering with the fuzz cases. The performance is being affected by other things going on the system. We can't guarantee that the same thing happens every time we run it because we're launching a new application. We're launching an application which is expensive as an operation itself. Just creating a new process on Linux takes a very long time. Just doing that is really hurting our performance. And honestly, that might be one of the reasons we're not scaling, is just running this program so many times is just not scaling. What would you use to measure what impacts perf on Linux? I would just put random timers around these things. I'd figure out where we're spending our time. I'd put a timer around this to see if we're spending time writing the file. I'd put a timer on this to see if we're spending time waiting to create or having the program run. I'd put a timer around our statistics if we have a significant amount of statistics tracking. In this case, we don't. So, are you aware of web app fuzzing that isn't live fuzzing? I mean, you could also put that in an emulator and do it in kind of an emulated context. Is emulation good enough in in terms of performance, it's typically always slightly better just due to your scaling properties. I pretty much only emulate to fuzz. That's basically the only way that I do it. So, I don't know. The emulation is typically only like 4 to 5 times slower than native execution in raw performance, and you very easily get that back. I mean, look at this. We're running 192 threads, and we're getting a 3x speed up, right? We were getting like 20 per second. Let's go here. Our single core performance is 30 per second, roughly. So with one thread, we're getting 30 fuzz cases a second, and with 64 threads, we are getting 60 a second. So would you rather have a 5x slowdown per fuzz case, but get a true 64x speed up, or would you rather get a 2x speed up? That's typically the argument that you're fighting when you're going against emulation. Because in a typical live environment or on a real system, you don't get enough control over the process to be able to reset or start new fuzz cases fast enough. So, can we get an H-top? Sure. We're just stuck in locks, right? It's like not even using the cores. We're bottlenecking on Python. Just a heads up. We're bottlenecking on Python in this situation. We're not bottlenecking on Linux. There's a reason why you're not supposed to write fuzzers in Python. It's a shit language. Heads up, most people write fuzzers in Python. Most of the crazy academic papers that are touting the most high-performance, crazy fuzzers are written in fucking Python, right? And they don't scale and they don't use threads. Hashtag not all papers. But in a lot of fucking situations, that's typically what it is, because the proof of concept's around an idea, not an implementation. But I would say for a lot of papers and for a lot of academic research, the implementation is the hard part. It's not hard to do something at one instruction per month and extract a bunch of information about what that's doing. It's hard to do that on multiple cores over the network without running into memory bottlenecks, without constraining by using a terabyte of memory per process that you're running and having exponential bloat or bottlenecking on I/O or the OS. Those are what I would argue are actually the hard problems. TLDR, if you extract more information from the program under test and you use that to influence the way you fuzz, you're gonna get better results. It's not a surprise. The surprise is if you can do that in a way that doesn't affect the performance of the fuzzer in such a negative way, or limit the amount of things that you can fuzz with that tool because it uses exponential memory with respect to the number of lines of code that you have in your target. C++ versus Rust versus Go. I like Rust a lot more. I don't like garbage collectors. C++ is a terrible language for safety and correctness and getting it right. Rust is just an amazing language all around. It's got a couple warts, but not many. Go has a garbage collector, and I don't like it. Okay. Hey, Ender, thank you so much for the Twitch Prime. Anyways, what about garbage collectors don't you like? They typically require that you have threads or different things that are running that you don't really understand how they work or when they run. Basically, the code becomes very non-deterministic in how it works. Different threads just start running at random times. Different things randomly get moved around on the heap at random times. Typically requires that you have objects stored in a way that they can be moved around at any time dynamically. I don't like it. I don't like when you don't understand when things are happening in the language because they're happening pseudo-randomly. I'm just not a fan of that. I thought modern C++ is memory safe. It isn't by default, which means it's not memory safe. Go try and get 1,000 developers at a company who have C++ experience to write modern C and never modern C++ and never slip into their old ways and do a couple static casts here and there. It's just never gonna happen. You can't have the ability for someone to do the quick and dirty thing because that's what literally everyone does. The amount of discipline that you need to have to use only the safe subset of a language is astronomical. It's just TLDR, it's never gonna happen. Will Rust kill low-level security? No, probably not, because people are going to use unsafe code because it'll make their allocator 2% faster, and they'll throw away all the security of the language so that they can get a 2% speed up on something that doesn't matter. And logic bugs, of course, but I would say there's still going to be a lot of corruption. Also, people aren't going to write a bunch of libraries in Rust, so it's basically going to be like people are going to write new things in Rust, but they're going to use image magic under the hood, which will always have infinite bugs. How do you feel about global allocators having to handle allocating in one thread and deallocating in another? How do you feel something like the mesh compacting allocator? I'm not familiar with that allocator at all. In terms of having the global allocator handle allocations on multiple threads, I think I'm fine with that. It's kind of standard that allocators handle the metadata themselves, where they kind of know where things came from or what nodes memory belongs to. Quite frankly, you can just make your allocator, you kind of need to do an OS, but you can make it where you can't really pass things between allocators. Skip, which thank you so much for the gifted subs. Too much software's been written in C and C++. Yeah. Don't shit on C. It feeds and funds the college education of many security researchers, and will do so for decades to come. Yeah, that's for sure. Mesh, if I remember correctly, merges disjoint virtual pages into the same physical page. Interesting. Is that just trying to get... I don't actually know what that's trying to really improve. Like, cache locality, maybe, but not that much, because cache lengths are 64 bytes. I don't think there's really much you benefit from by having it on the same page, because there's really not much stored at the page level. You have the TLBs. Oh, for memory usage? Yeah, I just don't care. I just buy more RAM. Memory usage is a solvable problem with money. In most, the amount of like micro optimization you get from an allocator is like 2 to 10% memory saving. It's literally like pennies to just pay that problem off. Okay. So we have our basic fuzzer here, but now we need to mutate our input. To do this, we need to make a copy. And in Python, I really don't actually know if this is going to make a copy. I think it will if I put it in a byte array, right? That'll make a copy, because I'll make a new byte array object. So this will create a copy of an existing input from the corpus. And now we're going to write one of the most complex fuzzers I've ever written. For blank in range random.randint 1 to 8. Up to 8 times. 1 to 8 times inclusive. We are going to, I guess since it's 1 to, oh, yeah, this will do 8 iterations. We are going to input random.randint 0 to lenimp is equal to random.randint 0 to 255 inclusive. And there you go, we made a fuzzer. And look at that, exited with -11. Do you know what -11 is? Do you know what is the non-negative version of 11? It's 11.